This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
So while we're setting things up, Tushar is a probability researcher doing quantum stuff. In a previous life, he used to live and breathe stochastic calculus and price and trade fixed income derivatives. These days, he's trying his hand at obscure algebraic geometry and some difficult PDEs, and he moved to academia so he could make less money but be a decent human being. And today, he's going to be talking to us about quantum algorithms for the Pathwise Lasso. And let me see. Do you is your mic on?
Is that?
Yes, perfect. And here's the clicker. And if you want to put this in your pocket, that way if you walk, it doesn't...
Yes.
Oh.
Timer.
So the floor is yours.
Okay. Can I use this?
Yes.
Okay. Hello. I am a classical guy, and one of the co-authors of this paper is here. So any quantum questions, we can defer to Debbie. But I'll try to answer your questions in any which way I can. Okay. So what is lasso? Lasso is a noun, and here it's a verb. And if you don't know what lasso is, we'll find out what lasso is. Okay, so the next. So high-dimensional regression, as everybody knows, is bog standard stuff you do in high school, and everybody thinks they know linear regression. And I never assumed I knew linear regression, because in high school you just plug in this formula, or maybe first-year undergraduate, assuming you have an equal number of observations and explanatory variables, right? So easy problem, no quantum here yet. What happens when you have more explanatory variables than the number of data points? Where would this problem arise? This problem would arise in a range of industries and settings. In genetics, you could have, I don't know, gene markers, millions, and you just have a few thousand data points. In finance, you would have more assets than the number of data points, and you're trying to find some regressor or some mean rate of return, or you're trying to determine the optimal portfolio. And when this paper came out, I had an email from somebody in Australia working for a mining company, and they were interested in this paper to implement some of the algorithms. So there's a wide range of applications where you're dealing with high-dimensional regression. So more regressors or explanatory variables, fewer data points. And that's the reality of what you have to deal with when you go into industry. So yeah, there's a lasso. Incidentally, how many people have seen or heard of lasso and know the meaning? So quite a few. Okay, so so there's a AI-generated image of a cowboy doing lasso, and that's the best I could do. And this was last year, and I believe this year it's a bit better. But anyway, I won't tell you which AI program I used. And the cowboy is trying to control these beaters because there are too many of them, so he's trying to lasso them in. So, okay, I'll give you a finance motivation. If you don't like it, you can think of your favorite motivation. Could be the number of restaurants that you have to choose and the number of times that you've actually experienced any of them. So that's a silly example, but here we're trying to minimize the L2 norm of this, where beta is, of course, not all zeros. And you want the L1 sparsity constraint so that by using the L1, you effectively force some of the betas to be zero. So that's basically linear regression, right? With an L1 norm. And in mean variance, sometimes what we do is we said, okay, we'll forget about the y, we'll just try and minimize this, which is, if you calculate this, this comes out to be the covariance of your portfolio, but you want to minimize the number of assets that you've actually invested in, right? So that's one particular example of using these kinds of models. And what we're seeking is, well, so let me go back here. This is just one lambda, but how do you determine an optimal path of lambda? So as lambda changes, you'll have different betas that are non-zero, which are optimal for that particular lambda. So what this paper is all about is seeking a quantum algorithm for the pathwise lasso, or the betas, as lambda varies. Okay? So that particular algorithm in the classical world is called homotopy, or LARS. LARS stands for least absolute regression shrinkage. That kind of makes sense if you think about it. And what we'll deal with is something called inactive and active sets. So for each lambda, so here's the algorithm. I'm not going to go through the details, but the general idea is that you start your iteration and you find the betas that are the most correlated, and then you keep on adding betas and for that particular lambda, and as you go to the next lambda, you might remove some of the betas or the explanatory variables. And so this is known as a classical algorithm. It's probably too much information to kind of see what's happening here, but you know, the slides are available, so you can have a look at the algorithm yourselves if you're interested or not. And so this is an example of, this picture is actually reversed. So we start with a high lambda, so the optimal solution is set all the betas to 0, and as you decrease the lambda, you'll see some of these variables becoming non-zero. And this picture is not so accurate because I couldn't find an example where a beta kind of comes into being non-zero and then becomes 0 again. But yeah, I mean, okay, so this one becomes non-zero, and then for this lambda it hits 0. So that's a particular sample path of the different betas as lambda varies. I think this is, I stole it from the original creators of Lasso at Stanford, Donahoe and forgot the names, but yeah, there's a famous paper that one day, which actually did this, proposed a Lasso path algorithm. So evaluating this optimal path is NP hard. You have to determine these kinks. It's an interesting problem. It's not motivated quantumly. It's a classical problem because yes? Okay, all right, fine, all right. And we're interested in whether we can come up with a speed up for this algorithm. Maybe it's a trivial task, or maybe it's not interesting, but I think it's interesting because people in industry are interested in these kinds of things. And since I come from industry, I think these kind of problems are interesting. So one of the solutions we used was to, rather than calculate the optimal beta, but approximate the betas. And the error is between the true beta for that particular lambda and, you know, within some error bounds, okay? So this is the quantum algorithm, which uses some techniques, but the main thing is the complexity of the total number of iterations is exponential, and it's a simple proof. For each iteration, you're checking whether the regressor should be in or out of your regression set, and then how many ways of choosing those regressors from the number of explanatory variables that you have left. And so these are the results that we have. It looks ugly. We're trying to clean it up, but anyway, approximate quantum laws has some sort of speed up. It's not bad, it's quadratic. Can we do better? Maybe. If we assume, so this is when the number of observations or the n times d matrix is fixed. But if we have a random matrix, we can do a bit better. And so, it's X is your design matrix, Gaussian, from some normal multivariate distribution. And then you can have some sort of exponential speedup. But in this very particular setting, the paper goes through a lot of technicalities using concentration bounds to get these results. So if you're interested in them, it might be a nice introduction for you, for people doing quantum who want to get into these kinds of techniques. Okay, so I think that's it. It's kind of linked to compressed sensing. Compressed sensing, you're trying to determine the optimal X matrix, minimizing the L1 bound. But I think the laws or the lasso pathwise is better because you can determine the actual optimal path. And when I speak to the algebraic geometers, they like this approach because, it's kind of an endogenous model of determining the optimal lambdas for the particular betas. And maybe one day, if some of you go into industry, you might be faced with this problem. So please look at this paper. That's it. Thank you.
Thank you very much for the great talk. We have a question on the left.
Yes.
Thank you so much. Great talk. And I'm also a statistician. So we sometimes also use the lasso algorithms to do some other, maybe for the other downstream analysis, because, for example, the lasso PCA or lasso CCA. Right. Do you think your algorithms can also accelerate some algorithms like lasso PCA or CCA, and also maybe elastic night, maybe the other penalty terms?
Okay, so if I heard the question correctly, you're talking about lasso PCA?
Yes.
Okay, yeah, I mean, sure, these are the basic algorithms, and future work could look at different types of lasso applications and algorithms. Sure, so you could use this work to speed up those things.
So everything about lasso, you can use quantum computer to accelerate. Yeah, it's very exciting. Thank you.
But implementation-wise, I don't know.
Yeah, cool. Thank you.
We have time for one more question. So I have a question for you.
Yes.
You mentioned that the bounds that you have are for worst case complexity, and I guess that random matrix are kind of like average cases.
Yes.
For some realistic problem, do you have any idea how close those are going to be to either average and probably certainly not random?
Well, so when we did the, so this is for a fixed design matrix. So this is the worst case, I guess. Yeah.
But I mean, in like a practical scenario, you don't expect kind of like worst case scaling, right?
Oh, right. Yeah. Yeah, I don't know. We're still trying to clean up these bounds because they look ugly. So it's, but the main idea was to get this, to show some sort of speed up and try to convince people that this is a huge problem in the statistics, genetics community and in other fields. And I think this is the first paper that actually tackles this pathwise lasso. Lasso is done. For fixed lambda, there are quantum papers, but not for a pathwise lasso. I must stress that. Okay, yes.
Okay, thank you very much. And then thank Tushar again.